Okay, welcome back, everyone. So the exciting stuff, right, where we get to see how the circuit works. All right, so we we built up this circuit. Just as a reminder, we're trying to factor 15 using this circuit. And what I'm doing is taking advantage of this box here, which implements this function. As you've seen in the discussion, in your first two lectures, quantum algorithms have to be, in general, these boxes have to be reversible. So what you have is X and W. So if we look at a little bit more detail about this box, X and W going into this box. And what comes out is X and W XOR F of X. And this F is the same function that we wrote up here. So these ones remain X, and these ones are encoding W XOR F of X. Okay? All right. So let's see how the circuit works. Step one is that we have, well, let's actually write down step 0 here and be explicit. Step 0 is here. Step 1 is immediately after the application of the Hadamard gates on the top 4 qubits. And then step 2 is measure just before the measurement, so immediately after the output of the box. And step 3 is right here, just before the QFT and after the measurement. So I'll call that step 3. And step 4 is here. And step 5 is here. So we're going to figure out what's happening in all of these steps. All right, this is exciting. Let's go through it. Step 0, we started off with all zeros. So I'm going to write down X and W like this. So when I write them in this order, X is on the left and W is on the right, okay? All right, so step 1. All the Hadamard gates are applied to the top 4 qubits. So the left part gets Hadamard applied to it, and the right part gets nothing applied to it. And this is a quick reminder about the sort of abusive notation that I told you about. What this is going to do is create the state 1/4, 0, plus 1, plus 2, plus all the way up to 15. I'm going to remind you that it doesn't generally make sense to write down states like this. And instead, what we have is a 4-qubit state, right? Every time you see 15 here, what it really means is 1, 1, 1, 1 in binary. So to differentiate between these and make it very clear what we're doing, to avoid any confusion, I'm going to write down 4 under each one of them. And what I mean is just this is a 4-bit representation of the decimal number that you see in there. So for example, 15 is the 4-bit number 1111. And I will put down 0 on the second one as well. But this one also has 4 next to it. Okay, so that's step 1. Step 2, now we go through the box. What does the box do? So I'm just going to write down exactly what we defined it does. It's 1/4, 0, so that's this first term. And then remember, we have this 0 out here. 0 XOR 13 to the power of 0 modulo 15 is what's contained inside this first qubit. All right, the second one, this first term. The second one is saying 1, so that's here. And then 0 plus XOR 13 to the power of 1 modulo 15. And so on, right? So there are many more of these terms. Now, let's look a little bit more closely about what these terms mean. But before we do, I would like to point out to you what some expression like this means. If you remember, plus with a circle around it means addition modulo 2. Or you might also know it as XOR if you're an electrical engineer. The thing to know about this XOR operation is that anything XORed with 0 is that thing itself. Okay? So all of these 0 XOR things end up just giving you the number itself. So I'm going to write things down a bit more explicitly by saying 1 over 4. So that first term is 0, 4, 13 to the power of 0 mod 15, plus 1, 4, 13 to the power of 1 mod 15. Remember to put the 4s down here. 2, 4, 13 to the power of 2 mod 15. Again, 4 qubits, and so on. What are these numbers? You've already looked at these numbers, right? These numbers we've computed before, and we found 13 to the power of 0 mod 15 cycles between, so 1 here, 13 here, 4 here, and there's one more where it cycles to 7. So if I write all of this out, all of the terms out, there are 16 of these terms. It comes down to the following. So 0, 1, 2, 3. All right? So that's the first 4 terms. And then we have 4, 5, 6, 7. And you can see the pattern emerging, right? The first section is going to be increasing. So there's going to be an 8 here, a 9 here, a 10 here, and an 11 here, and a 12 here, a 13 here, a 14 here, and a 15 here. And this is repeating. It's 1, 13, 4, 7, and 1, 13, 4, 7. The reason why I'm paying this much attention and writing down all of these numbers is because I think it's important the first time you're seeing Shor's algorithm working to see all of these laid out in some good detail. All right, so this is what the X and W register look like after the application of that box that we drew in our circuit. So now we're at the output of at that box. Then the protocol tells us to do a measurement of the bottom 4 qubits, the W register, okay? So remember, the ordering here is X is the left one and W is the right one. If you were to measure the state, so let me write down explicitly, step 3, measure the W register. What are the outputs? What do you think happens if you do the measurement of the W register? I think it's very good to pause for a second and think about what the outputs are. And I hope you're not surprised if I tell you the outputs of W, if you were to measure it, are either 1, 13, 4, or 7, right? There are no other outputs. In this case, you can only get those 4 outputs. So let's say for the sake of going through the rest of the circuit, let's say we measured 7. And I would encourage you as you're going through these lecture materials Yes, that's exactly right, Aditya. It's 1 or 13 or 4 or 7 with equal probability. Let's say we measure 7 for the rest of these discussions, but as you go through this material, maybe try working through the rest of this work with a different measurement, maybe 13 or 4. So if you measured 7, that means what you're doing is effectively measuring this part, right? So what happens to x when you measure 7? So after measuring 7, x becomes, what does x become? Well, if you measure 7, x could take on the value of any of these 4 values. So really, x becomes either 3 or 7 or 11 or 15, right? And x becomes this part, and x and w becomes 7. So this is what these look like. I hope exactly. I see all of you making this comment that we get 3, 7, 11, and 15 with equal probability. That's really nice. The one thing I want you to take note of here is that the normalization has changed. So previously we had 1/4 because there are 16 combinations. Here we have only 4 combinations. So we have 1 over square root of 4. Okay. Note the change in normalization so that you remember. All right. So what does this mean now? Notice that I have 7 out here and I have these terms here. I'm going to, for a moment, drop the 7 because it's just going to be at this point a constant multiplier to all the terms. And as you see in the circuit, I don't care anymore about what that measurement output is. I'm now interested in applying a QFT dagger to the top 4 qubits to the X register. So I'm going to apply, so step 4, apply QFT dagger on the X register. And so I'm going to drop the W register for a moment as I do the QFT because it purely affects working with only the X register. I'll remind you again. So QFT is going to take X and turn it into X tilde, as we discussed before. And that is 1 over square root of n, sum from y equals 0 to n minus 1, e to the 2 pi I over n, x times y, and y inside here. So QFT dagger, it's going to take x tilde back into x, and the way that's going to work is by doing y equals 0 to n minus 1 again, e to the 2 pi I over n, x times y. There's going to be a y here. The main difference is, remember, you're trying to do this dagger means complex conjugate transpose. It's going to turn this into a complex conjugate, and I hope you're not surprised. What that means is putting a minus up there. So turning I into minus I is all that does. So what does QFT do when we apply it on the X register? Well, there are 4 terms. We need to worry about what QFT dagger of 3 looks like because we have a 3 down there. We need to worry about what QFT dagger of 7 looks like. We need to worry about what QFT dagger of 11 looks like. And we need to worry about what QFT dagger of 15 looks like. And then we can add all of them up here, as we see. And we can take a multiplier out here. But for the moment, let's just focus on what these QFT daggers do. For 3, what it's doing is saying 1 over square root of 16 in this case, because we have four qubits. Sum from y is 0 to n minus 1, e to the 2 pi I with a minus sign in front of it. X is 3 now, right? So 3 times y over 16 y. That's QFT dagger of 3. QFT dagger of 7 is looking exactly the same with this change, e to the 2 pi I with a minus 7 times y over 16. The one with 11 looks like this. And the one with 15 looks like this. And the reason why I'm showing you all of these in so much detail is so that next time you're working with maybe a different set of numbers, you have a good starting point to look through numbers and compare. So QFT dagger of X itself, which was the sum of all of these numbers. So there's a half in front that you need to worry about, and 1 over square root of 16, which is a fourth. Together they make an eighth. And you have these sums. N minus 1 is 15 in this case. So I'm going to erase that and write 15. So the first one is, so I'm going to write down this one as in a most simplified form that I can write it. It looks like this. The second one looks like this. The third one looks like this. And the fourth one looks like this. And all of these are prefactors to a y multiplier. So these are just numbers that we need to add up. Now, adding up these numbers, so let me just remind you, e to the I 3 pi over 8y is cosine of 3 pi over 8y minus I sine of 3 pi over 8y. And the same for this one and this one and this one. And you can add up all of these numbers. And I have written down a piece of code. Maybe Susie, I think this is a good time to share screen from my computer. So I'm going to share very quickly.
All right, you should be all set to share.
Thank you, Susie. I hope you can all see on the screen, I've written down a quick piece of code to compute all of these. You can also do it by hand, but what I wanted to do is show you how all of these terms, so e to the minus I 3 pi over 8y, e to the minus I 7 pi over 8y, 11, and 15 pi over 8, when you add all of them up, these are the numbers that you get. So they're all, so we're doing this for all y's, right? Y going from 0 to 15. Look at how for most of these, the sum is 0. And so what that means is only a few terms survive. So 4 of these terms survive. And so let's stop sharing now and go back to our iPad and start writing down what that sum becomes. So at the end, the terms that survive are the case when y is 0, when y is 4, when y is 8, and when y is 12. And they have some coefficients in front of them. So this is 4, this is 4i, this is minus 4, this is minus 4i. Okay, so that's a lot of algebra, but at the end of the day, I want you to pay attention to two things. So here's an interesting point to take note. Notice how this sum, I'll circle it here. This sum was running all the way from y equals 0 to y equals 15. Because of all of these terms adding up, the only terms that survived are the ones that are either when y is 0, 4, 8, or 12. All the other terms vanished because you had equal contributions of plus and minus. And so what does that mean? This is exactly what it means when people tell you quantum computers take advantage of interference. So interference in this case is the situation that we have here where a lot of the terms vanished and the answer only converts to the terms that we care about. Okay? So what does it mean at this point now if we go back and look at the circuit? Let me show you again where we are. We just did the quantum Fourier transform, and now we're at this point where we're ready to measure the X register. So what happens if we measure the X register? What do we get? So this is the last step, right? Step 5. What happens if you measure this state? Maybe I'll pause for a second and wait for all of you to make some guesses. What do you think we'll get? I hope you're not surprised when I say the only possible outcomes are exactly. So Amir, you have that exactly right. Jeremy as well. So you get either 0, 4, 8, or 12 with equal probability. And that's it. At this point, I'm really happy that all of you are replying 0, 4, 8, and 12. At this point, you've done the quantum part of Shor's algorithm. What remains is now the classical post-processing. So now that you've measured 0, 4, 8, and 12, remaining steps are all classical post-processing. And so you can do all of this part after you've taken out of the quantum computer on your own classical computer. Remaining steps on classical post-processing. And I hope it's not surprising to you, independent of what results we're going to get after doing all of this post-processing, you can kind of already see the answer coming out, right? You can see that periodicity is showing up in these numbers. So the difference between them is 4, right? The difference between them being 4 is exactly what we've done by taking advantage of Shor's algorithm. So all of this math, we just went through all of these calculations, but you see how the problem was a very simple question, factor 15. It blew up into this very large kind of computational problem where we got a lot of numbers. But in the end, it boils down to extracting these numbers, 0, 4, 8, or 12 from the quantum computer. But remember, you don't get 0 or 4 or 8 or 12 at the same time. When you do your measurement, you get one of these numbers. So you get either 0, or you get 4, or you get 8, or you get 12. So let's think about what would happen if you had the result of maybe 4, or 8, or 12, or 0. So let's analyze what happens for each outcome. And this is the important takeaway from the analysis I'm about to show you. It's important to note that the measurement results, I'll write this in red because it's worth emphasizing. The measurement results peak for Shor's algorithm near j times n over r for some integer j. So what does that mean? If, for example, if we measure 4, remember r is the period that we're looking for. If we measure 4, for example, and I'll remind you again, this is 4 measured from 4 qubits. Then j times n in this case, because we're doing 4 qubits, is 16, 2 to the power of 4, over r is the number that we measured. And this is true, for example, only if j is 1 and r is 4, right? So this is one solution to the problem. Of course, there are multiple values of j that would make this work, but this is the lowest one that would work. So this tells us that r is 4, and r is 4. Is that good? Yes. Well, remember the protocol from before. Is r even? Step 1. Yes, so that's good news. The second step, is x, which is defined as a to the r over 2 modulo n. Who is that? That is, for example, we started off with 13. 13 to the power of r over 2 modulo 15 is 4. So can this possibly give us the factors? Well, x plus 1 is 5, x minus 1 is 3, and GCD of x plus 1 comma n and x minus 1 comma n is exactly GCD of 5 and 15 and 3 and 15, which should give you 5 and 3. So if you were to measure 4, you can immediately extract the factors 5 and 3 from this process. Okay, so that's exactly the same analysis that I showed you before, except now we're using the outputs from the quantum computer to do this work. So if r is 4, we're able to back out those factors. That's really cool. And I hope you're impressed that going through all of this can get us those factors. If r is 8, what do we do? Well, again, I'll say j times 16 over r is 8. What are the possible solutions for this? Well, either j equals 1 and r equals 2. Those are possible solutions. Or j equals 2 and r equals 4. So first of all, notice that if r equals 4, we're back to the case above, so this works. We already get the answer from there. If j is 1 and r equals 2, let me show you what happens. X is going to be, again, 13 to the power of 1. So that's r over 2. 2 over 2 modulo 15. That's going to be 2. And x plus 1 and x minus 1 are 1 and 3. And the GCD of x plus 1 comma n is 3, 15, which is 3. And the GCD of 1 and 15 is just 1. So this one leads you to a partial solution, right? So this partial solution is exactly what tells you that you can back out at least one of these factors. So you go and try whether 3 is a number that divides into 15, and once you confirm that, you can take advantage of 3, that answer that you found, to find the other factor. So you can do 15 divided by 5, divided by 3, and find 5. Okay. Let me reiterate again, because I see some questions coming into the chat about this. What I'm saying here is Shor's algorithm is telling us that the measurement results peak near j times n over r. What that means is all of these measurement outcomes, either 0 or 4 or 8 or 12, are equal to some factor j, some integer j, some multiplier j, times n over r. Remember, n is 2 to the power of n, the number of qubits. Okay? All right. You can go through exactly the same calculation for the case when r is 12. So remember, the possible measurement outcomes were 0, 4, 8, and 12. So if r is 12, what happens? J times 16 over r is 12. What results make that possible? Well, either R is 4 and J is 3, which gives you back exactly the results that we had above. So remember, we had R is 4 working here, works and gives us 5 and 3 as factors. And note that in all of these, I'm checking if R is even, right? We did this earlier. If you need to, maybe later on as you're reviewing the notes, I want to remind you, we wrote down these rules. If R is even, I'm continuing and computing this x, which is a to the r over 2 modulo n. And then I'm saying if x plus 1 is not equivalent to 0 modulo n, then the p and q values, at least one of them, is contained in these numbers. Either it's x plus 1 and n or x minus 1 and n, the greatest common divisor. Okay, let's go back to the end. So what I'd like to tell you from all of this analysis is that in the case where you measured, so final result, quantum computer told us either the outcomes 0, 4, 8, or 12. And these were 4-qubit outputs. We took these, and with the case of 4, we were able to get the factors 3 and 5. With the case of 12, we were able to get the factors 3 and 5. With the case of 8, we got this partial solution, but that's still something we can take advantage of, right? Because you got one of the factors, it's trivial to find the other factor. So we got 3 and 5 that we can leverage from taking advantage of 3. 0 is the answer that doesn't lead us to anything, right? Because j times 16 over r equals 0 doesn't give you any information. So 0 is the case when you have to try the experiment again on the quantum computer. So if we ever get 0, we have to try again. And remember, all of these are equally probable. So 0 is just as likely as any of the others. So it looks like 3 out of 4 of the results work for us. And we are able to extract the factors.
Hey, Abe.
Yep.
It looks as though some folks are wondering about whether R is even or odd and what kind of difference that makes.
Mm-hmm.
So it just looks like that's a large question that's being asked in the chat.
Okay, so that's a good question. Let me take you to the rules that we wrote. If R is even, you can compute this value x that you need to find the factors because you need an r over 2 in the exponent. That's the main problem that you're going to have. If r is odd, then you no longer have something that makes sense. That's why we're making sure that r is even before going into all of this. So I hope that answers that question. And really, what I want to do here is show you how we've gone through this exercise of making the quantum computer do the work of giving us those numbers 0, 4, 8, and 12 that then we could classically post-process. So take the numbers out of the quantum computer and process them and find these factors 3 and 5, okay? So I want to pause here very quickly and set up my screen for sharing with you a result. So let's take a moment here. Maybe while I'm setting up, all of you could ask questions that you're thinking of, and I'll set up here, sharing my screen. Let's see. Share screen. So the paper that I'm sharing with you here on the screen is the first demonstration of Shor's algorithm. And this is work that was done jointly between IBM and Stanford. And this work was done experimentally using nuclear magnetic resonance. And this was how the first demonstration of Shor's algorithm happened experimentally. So I'll click PDF and just walk you through the paper very quickly. But what's exciting to see is that now you can go through this paper and understand everything. But more importantly, let me show you just some of the results. Let's see. So this is exactly the kind of circuit that they use to do the work. So you see there's some detail here that involves the way the gates are applied in that particular system. But immediately you can see the way they're doing the work is, again, so they have this box that applies a to the x modulo n. They apply Hadamard's on the top qubits and do an inverse quantum Fourier transform. This is exactly what we discussed today. And so you should be able to read through this paper. And while the specifics of the molecule they used, of the details of the experiment might be something unfamiliar, the core of how to build this particular quantum algorithm is something that you can look through this paper and really see how experimentally these things are really hard to build. And the sheer amount of engineering that went into making this happen is something that's worth looking through. Okay, let me just stop sharing this very quickly. And this will be one of the documents that we share with you in the Discord today. Maybe Susie, thank you. Oh, you read my mind. Okay, so we went through all of these exercises that I hope inspire you to maybe work through it again one more time on your own. There is a lot to digest here. But at the end of the day, big picture, what did we do? We had a quantum computer which did quantum phase estimation with the kind of gates that allowed us to do this function f of an of x. We fed that quantum computer a specific set of qubits, all of them in the 0 state. Several qubits. We did n for the input and m for the target. And we were able to get results out of that quantum computer that had n qubits. And then we took these results and then post-processed them on a classical computer. Okay. Now, I mentioned to you earlier that there are some caveats that we need to talk about in terms of how this is all implemented experimentally. And I can discuss those caveats now. But before I move forward, let me just make sure there are no questions that have come up about all of this work that we just did. Are there any questions, Susan?
There are. It seems though that they aren't relevant to this information, but maybe some from the past. Would you still be up for answering some of them?
Sure. Let's take a couple of them. And if maybe they're too far away, I'll just move them to the Discord.
Cool. Can you explain how QPE is applied to quantum chemistry calculations?
Oh, absolutely. So in quantum chemistry, one of the things that you're interested in is dynamics, so time evolution. And you'll find that quantum phase estimation is effectively helping us. Hamiltonian dynamics, for those of you who are familiar with quantum chemistry, is unitary. And so you can use that unitary that comes from your Hamiltonian to do simulations in chemistry. So this is just the big picture kind of zoomed out perspective. Can we take any other questions?
Yes. If we have picked a number which isn't co-prime, then we don't need to do Shor's algorithm as we have already found P or Q, do we?
Yep, that's exactly right. If A, the number that you pick randomly, happens to be not co-prime with N, that means you have a factor common with N that you can then use to find the other factor. So you're done. You don't need to go through Shor's algorithm. However, that is very unlikely, right? That's like looking for a needle in a haystack. The chances are much, much higher that you'll find something that is not coprime with n. And just there are documented numbers that show you the likelihood of finding an A that is coprime with n. It's highly unlikely.
Cool. And then maybe one or two more. It looks like it appears that quantum algorithm now is still very low level as compared to classical algorithm design, where we might deal with abstractions. Do we foresee quantum algorithm design transitioning into a higher level perspective in the near future?
Okay, so this is a good question, and what I would strongly suggest is taking a look at Qiskit Aqua. So Aqua is Qiskit's application layer. And so you abstract away from the details of the quantum circuits and use effectively building blocks that make up several different quantum programs. So one of the things you can do in Aqua is immediately call a function called Shor. So you can do Shor's algorithm very quickly using Aqua. But what that also means is you don't care about the details involved in Shor's algorithm, but you can use it as a box in other algorithms. What I would ask, though, is that because you're going to use this block in other algorithms, maybe it's worth looking into the detail of what this box is doing the first time you're learning it, and that's why we're going through all of this learning material. I hope that's helpful.
Right. And it looks like the people want to know, where did you get that JN over R?
Yeah, so that's a good question. So this is one of these results that would require a lot more detail to go into. So it's hard to derive here within the short amount of time that we have. And so what I'll do is point you to a reference that allows you to see exactly how that's derived. Within the context of the work that we've done, it's maybe not as important to focus too much on those because they have number theory prerequisites that are not necessary for the work that we're doing. But if you'd like to learn, I can point you to some references that show you exactly how those come out.
Cool. It looks like those are the most upvoted questions right now. I think we can get back to the last 15 minutes or so of your lecture.
Okay, awesome. So we've come all of this way. Let's talk about the caveats of the circuit that I showed you. So I'll put down explicitly caveats. Remember, the register for X had n qubits above. And it had n qubits because the number we were trying to find, so it had 4 qubits because the number we were trying to find is n equals 15. And 15 can be expressed in binary like this. It's a 4-bit number. That's why we chose n to be 4. In a more general case, this case is very specific and tailored to 15. In a more general case, we need 2n qubits for the input register instead of n qubits. That's one caveat that I'd like to tell you about. And the reason is that these numbers that you saw, the modular exponentiation, we didn't have more than 4 numbers in that modular exponentiation. So that's why we were able to do all of this work with 4 qubits. In the case of larger number of qubits, so different, more general cases, you would need 2 times n. General case, we need 2 times n qubits for the input register. So this is immediately going to show you why it's so difficult to implement Shor's algorithm, right? So if n is a 1,000-digit number, here we're playing with 15, but if n is a 1,000-digit number, I just told you need 2,000 qubits to do the work. And we're not anywhere near that level of having that many qubits. This is why Shor's algorithm is so hard to implement today on a quantum computer. The second caveat I'd like to tell you about is going through this process that we talked about. Is R even? If r is even, then is x to the power of r over 2 plus 1 equivalent to 0 modulo n. All of these processes will, with probability greater than a half, r will be even, and a to the power of r over 2 plus 1 will not be equivalent to 0 modulo n, which means you will be able to extract those primes. So with probability at least a half, we should be able to get success going through this process. Okay? Those are the caveats that I wanted to mention to you. And I would say for a more detailed discussion of exactly how all of this works, I would strongly recommend going through the Shor's algorithm section in the Qiskit textbook, or the Shor's algorithm discussion in Merman's quantum computer science book. So Merman goes through the number theory prerequisites that are necessary for you to answer questions like the one that came up earlier about Jn over R. Okay. So one last thing before we conclude this lecture. Let me take you back to the circuit that we built and analyzed, okay? I showed you this circuit, and I mentioned that the blocks that we're using are all in this circuit. We have Hadamard gates. You know how to implement those. You have a QFT dagger here. You know how to implement that now. You have a measurement. You know how to do that at this point. And you have another measurement here. What I haven't told you so far is how to implement this gate, this UF of AN. I haven't told you exactly what's contained inside this box. And what I want to convince you, if you remember, I've already kind of given you the answer, is that Shor's algorithm is quantum phase estimation in disguise. I want to show you exactly how what you're seeing here is quantum phase estimation, okay? So let's write down, this is the part that when I learned it the first time, everything kind of made sense about why we're learning things in this sequence. Let's talk about how to implement UFANN, okay? I'll just remind you very quickly, recall that FAN of x implements the function a to the x modulo n, okay? And remember, x really is just the decimal representation of something that looks like this. And so the decimal representation is 2 to the power of n minus 1 x1 plus 2 to the power of n minus 2 x2 plus going down all the way to 2 to the power of 0 of xn. Okay? So I can rewrite f, this definition that I gave here, by saying FAN of x is equivalent to a to the x modulo n. What is a to the x modulo n? That's a to the, so x is 2 to the power of n minus 1, x1, 2 to the power of n minus 2, x2, 2 to the power of n minus 3, x3, going all the way down to 2 to the power of 0, xn. Okay? Now, this is a series of sums in an exponent, so you can write them down as products. So this is a to the power of 2 to the power of n minus 1, x1, a to the power of 2 to the power of n minus 2, x2, going all the way down to a to the power of 2 to the power of 0, xn, modulo n again. You should already start seeing something that looks very familiar. The way to implement this is the following. So this is x1. This is x2. And going all the way down to xn. and you have your m qubits here for the target. The way to implement this, notice there's an x1 at the exponent, x2 at the exponent, xn at the exponent. Those things tell you that this is a controlled operation. So you have something here that looks like a to the power of 2 to the power of n minus 1 modulo n. Here you have a to the power of 2 to the n minus 2 modulo n. And notice that the exponent doesn't contain x1 and x2 anymore, right? The way I'm implementing it is by doing these controls, going all the way down to a to the power of 2 to the power of 0 modulo n. So that's how you'd implement that box. And this kind of schematic looks exactly like what you've seen in quantum phase estimation. And so this is why I tell you Shor's algorithm is quantum phase estimation in disguise. Really, the unitary operator is a to the power of 2 to the power of x modulo n, and you're applying different powers. So u to the power of 2 to the power of x that we used to write for quantum phase estimation is really a to the power of 2 to the power of x modulo n in this particular application. So that's it. That, I hope, convinces you that we have quantum phase estimation. When you take this block that I've shown you and put it inside the circuit that I've built so far, which is this one, you see that the schematic is exactly quantum phase estimation. Hadamard's at the beginning. Start with a state that is an eigenstate of the operator. Do a series of modular exponentiations. That's the term that people use in the literature. And then do a measurement and undo the QFT, undo the results with a QFT dagger. So I hope that convinces you exactly how all of this is implementing Shor's algorithm, but really it's a QPE that you've already seen in disguise in a different form. So I'll explicitly write down, take a look at the Qiskit textbook chapter. On Shor's algorithm to see how modular exponentiation, so modular exponentiation is just a fancy way of describing these operations, is implemented using gates. And in fact, the focus of your lab today will be factoring 15, and you'll factor 15 by building out this exact circuit, doing modular exponentiation, doing the initialization with the Hadamards at the beginning, and so on. So I hope this is helpful in terms of understanding how all of this is built together, and I hope you've gotten an insight into how Shor's algorithm works. So in the past 2 lectures, we talked about Shor's algorithm in a lot of detail. We built up the prerequisites for it. So we needed to build up intuition on quantum Fourier transform, which was then built into quantum phase estimation, which really is what Shor's algorithm is in disguise. So I hope this chain of discussing all of these materials was helpful to you and that you found it insightful. I'm really excited for your lab because when I was learning all of this, I didn't have access to just be able to implement things in code. You are going to have that chance, so please work on the lab. And I think this is a good point to conclude. Thank you, everyone.